Hello, my name is Xavier Monteys, Senior Geologist at the Geological Survey Ireland. I'm going to briefly unveil some of the insights in how we monitor coastal change from space, primarily from satellite, but with some links and reference to airborne and advanced land mapping techniques. This is relevant in the marine context we are here today, as the near-shore environment, the intertidal and down to the surf zone especially, are often the more dynamic and challenging and unmapped areas in the world, in Ireland, for instance, and they are precisely a key component in understanding coastal processes and the associated changes. We're going to go over some background information on coastal change, then on how we measure these changes using images, to finally see some examples and applications. We can see the Sentinel-2 constellation here, which is composed of 2 satellites, how they track to cover every inch of the Earth, which normally takes approximately 5 days. In Ireland, we have repeated surveys every 3.5 days. This high temporal resolution has revolutionized the way we monitor our coasts. It's primarily the power of the sea that has shaped Ireland's recent coastline into what we can observe today through the various coastal processes, including erosion, transport, and accumulation of sediments. Some of the processes of coastal erosion operate at several scales, not just on the physical, but also on the temporal domain. Some processes just take hours, like tides, or days, for instance, storms, years to decades, like the North Atlantic Oscillation, to millennia, more like on the geological process, such as the tectonic movements, and also threats of like the sea level rise from short to long term. Typically, coastal change happens gradually by a combination of these factors and processes. But big changes mainly take place after unique events, such as storms or storm surges that can have significant impacts in very short time windows. So again, if we want to understand what happens to a particular area, we have to be looking at past records and correlating them to events, so we can better model the coastal processes. Erosion in the coast takes place when material is removed and carried away. Well, the result is quite simple to understand. The drivers can be complex. Ireland is quite a unique place compared to mainland Europe because large parts of our coastline, particularly on the East Coast, were shaped in the most recent Quaternary age under glacial conditions. As a result, we have soft sediments, till and gravel left behind by the glaciers, and these are not compacted, so making it very easy to be eroded. These, combined with increased storminess and higher water levels that we are seeing today, make large areas of the coastline susceptible to be eroded. Here you can see a few examples from Portland where active erosion has been going on for decades, and that has been increased recently. Kilpatrick Ridge in North County Wexford, which is a European recognized habitat for wildlife. This has been destroyed in the recent storms and has been endangering nearby homes. Poland Strand in County Donegal, where in 2020, approximately 50 meters of the coast were wiped off and also affected the nearby pathways. Coastal accretion on the other side is the deposition of sediment, usually sand, which is evident by the seaward advance of a shoreline indicator. Though it's important to recognize that while the process can be considered inverse to erosion, the results are different from the original, as the accumulation is generally loose and unconsolidated. So it forms a pit on a part of the beach, for instance. We can see Bull Island, a 5 kilometers long sand pit on the north wall of Dublin Port, developing following the construction of the north wall during the first half of the 19th century. Since then, it has grown, showing aggression for many years. However, nowadays, erosion is happening in the north and even more accentuated after the storms. So any human intervention in the coast is likely to have some impacts, and this is a good example that we are seeing here. When walls or coastal defenses are implemented, they might protect a cliff at that precise point, but it might cause even more erosion in adjacent areas or sediment starvation on a place nearby. Another important aspect of coastal change, sometimes neglected in studies, is the change of land cover and land use. Land cover maps are a basic sort of information to track the impact that human activity, natural processes, and climate change have on coastal areas. A pioneer of that was the Korean land cover inventory, initiated back in 1985, with several updates till now, 2018. While the Copernicus Sentinel-2 mission delivers ideal images to map land cover, but producing huge amounts of time series data that have to be processed. To make this possible, the ESA funded the Sentinel-2 for Science land cover project, which explored novel cloud computing technologies and machine learning to automate this mapping. As a result, Europe land's cover has now been mapped, showing 13 land cover classifications, which they can be used to inform other applications. Coastal managers use land cover data and maps to better understand the impacts of natural phenomena and human use of the landscape, such as coastal flooding or storages. So they're very powerful when looking at change of land cover. Let's see how we monitor changes along the coast, what methods we use. We can do topographic surveys to detect changes on elevation profiles, from GPS to mobile mapping systems that include LiDAR and optical cameras. Data collecting using this technology has allowed us to build accurate elevation models on the coast so we can monitor 3D change over time, and ranging from millimeters to centimeters of accuracy. Airborne surveys allow us to map large areas in very short time windows using photogrammetry or LiDAR, and then work in a similar fashion than previous methods, calculating 2D or point cloud volumetric changes. So large areas, but to a higher cost. We are here in the tens of centimeters of accuracy. Satellite monitoring techniques, such as the latest ISA coastal erosion GSIs involved, allow us to map even larger areas and longer time spans since the 1980s. However, to a lesser degree of accuracy and only in 2D. So mapping shorelines to measure coastal migration. We are here on the meter resolution. The advantage is that satellites do not stop and keep us providing with good quality measuring. And also, very important science, for example, with dedicated apps which allow the local community to add information about erosion events happening near their homes. A powerful concept to understand when monitoring from the space is the spatial resolution. Satellite digital data are scanned from an area coming out in the form of individual image points, so-called pixels. Pixels can be defined as the smallest area unit in a digital image. The size of the pixel determines the spatial resolution of this image. Spatial resolutions can vary from centimeters, for example, military sensors, to kilometers, meteorological satellites. In between, we find the ones that we normally use. Here we have an example of 4 different spatial resolutions for typical optical satellites. The same location for TRAN, we see how different resolutions allow us to see coastal features in more detail. For monitoring coastal change, we typically employ resolutions of less than 10 meters. However, for other applications, such as land cover, resolutions can be more adequate if they are larger. Sometimes there is less interference from adjacent pixels. Let's dive now into how we measure shoreline change from images to illustrate what exactly are we monitoring. Shoreline change has been measured from a series of images, including orthophotos and satellite, where the coastline, for instance, the vegetation line, has been digitized. This is an example of a shoreline digitized in North Dublin between 2000 and 2020. The total number of shorelines used vary at locations depending on image availability and accuracy. Parallel transects perpendicular to the coastlines are then drawn from a defined baseline. These transects intersect the digitized lines at fixed points that the system will use for calculations of distance over time. Then it uses a weighted regression model that quantifies the magnitude and direction of the change, so whether it's accretion or erosion, and identify cyclical trends. Let's now have a look at the results from the larger Northern Dublin area, an example of calculations in Rush Portran, where erosion rates have been a concern for a number of decades. In recent years, coastal erosion has accelerated and the seas are starting to get closer to private property near the beach. We've measured shoreline change looking at data back 25 years. The level of change is not constant and it varies from few centimeters to meters every year. We can see how the erosion, here displayed in red, in the south part of Portrane, while accretion is happening just on the northern part in the estuary. There are hotspots in the borough and North Portrane with erosion rates, they range between 2 and 4 meters per year, so quite severe. And it's also significant to note how in the last 5 years, there's been an increase in the rate of this erosion, which up to 5 meters a year. For that reason, the area is currently under complex coastal defense strategy coordinated by the local authority and the OPW. This is a clear example where detailed monitoring of coastal evolution is key, particularly in vulnerable areas, to obtain success in future adaptation plans. It's important to note that we can also measure coastal change employing other remote sensing methods, independent from the image-based method displayed before. In this case, the target is to delineate the foot of the cliff using automatic algorithms that detect changes in curvature. We use digital evaluation models from different years and measure the migration of these lines perpendicular to the coast over time. And this is in fact one of the best proxies for measuring true erosion at the foot of the slope. The difficulty resides in finding good quality digital elevation models. The results then can be used to validate the image-based approach we've seen before. One of the climate-related products GSI has been recently developing, receiving inputs from the coastal erosion outputs we've seen before, is the CVI thematic map, Coastal Vulnerability Index map, showing ranges of vulnerability from low to high for every point of the coast, depending on whether a particular area is more or less susceptible to change as sea level rises. Some of the advantages of applying an index-based approach resides in the clarity of the results, so this map can be used as a starting point in the adaptation process. This map has been recently featured in the new Coastal Atlas of Ireland, which provides me the perfect excuse to close the presentation with a cover of this atlas led by the UCC Press, a titanic effort that has placed the Irish coast on the front page of every home in Ireland. And with this I finish, and thank you for your time.